So as you can see, make it a little bit larger. This is the whatever we had already on the slide, and this I'm gonna also do that. And this was our pivot, and we find the position of it. I'm gonna highlight it like what the book did. So we're done with this one. We find its own position. Now we have two lists. One of them is this one. So I'm going to make this thicker, and then one of them is the other one. So I have two lists. We're going to do the partitioning on both of them. So first, this is going to be my pivot. This is going to be the low index, and this is going to be high. Same thing is going to happen on the other side. This is going to be my pivot. This is going to be the low, and this is going to be the high, right? So we're going to keep going. So we have to do the partitioning algorithm on this one, high and low position, find them. And so whoever low pointing to it now has to be the less than our pivot. Whoever high pointing to it has to be bigger than our pivot. We started with low. 2 is less than our pivot. We're good. We increment the value of low. Low pointing to 1. 1 is less than our pivot. We're good. Low pointing to 3 now. 3 is less than our pivot, so we're good. Now my low and high basically the same, and that's fine. So now low pointing to the 0. 0 is less than our pivot, we're still good. So we're going to increment the value of low, and that value of low is basically going to pass the size of this tree. There's no more things to compare, right? So it's going to be done. We're done with. And also look at that. High, we're going to go back to high. High is pointing to 0. 0 is bigger. We expect it to be bigger, right? Whatever high pointing to, we expect it to be bigger than the value of people, and it's not. So this is our objection. So high is straight right there, and low is already passed. We're done with low. Low passed this entire array. So as you can see, low and high passed each other. So there's no more element to compare. And so we're going to stop. And high now is pointing to the position that the pivot belong to. So we have to do the swap. So this is how we're going to do the swap, right? The value of whatever high pointing to it and the value of the pivot are going to swap. So that means 4 is coming here and 0 is going to go right there. So we find the position of the pivot and we divided the list. I'm going to just write the list again here. So we find the position of the pivot. We divided the list to the half, right? This is one half of it. The other half is 0, right? So we were not lucky. And so we find the position of the pivot. Now we have this a list that we have to do the same thing with it, right? So I get rid of the other 2. You're going to do the same thing. So this is going to be my pivot. This is the value of low. This is the value of high. A little bit of cleanup here. So pivot, the low has to point to an element that are less than our pivot. That's not the case, so that's our objection. We're going to stop right here. We go to the high. High should point to an element that is bigger than our pivot. That's true here. So we're going to decrement the value of high. Pointing to an element that's bigger than pivot, we're good. Pointing at, we're going to go right here. It's also pointing to an element that's bigger than our pivot, so we're still good. So we're going to go right here. And low is past and low past each other. So we stop right there. We cannot do anything. Whoever high point to it is going to be the position of the pivot. And so that means we don't have to move anything. We don't have to even swap, because basically the pivot was its own position in this list. So now we did divided this list, but again, we were not lucky, and the list has become only divided by 2, but one part of it is 0, and the rest of the elements are in the other side. Basically, it's divided by, didn't divide it by half, it's just reduced by 1. So we're going to have now this list, we're going to do the same thing. So this is my pivot, this is the value of low, this is the value of high. So low pointing to 1, and that's less than our pivot, we're good. We're moving to next one. Low pointing to 3. 3 is bigger than our pivot. We don't like it. So we're going to stop right there. High pointing to 3. 3 is bigger than our pivot. We're good. So we're decrementing the value of high. High is pointing to 1. And we don't like it, because we expect to, whoever element the high pointing to it is going to be bigger than our pivot. And in this case, 1 is not. So we're going to stop right there. But look at high and low. They passed each other already. So high is not past low. So that means we don't have more element to compare, and that means we find the position of the pivot. And then we have to do the swap. So 2 is coming here, 1 go there, and we find the position of the pivot. So now we're not too lucky again, and the elements are going to only be, break with, actually, this one we're lucky, right? So we divided exactly by half. Sorry about that. So we actually were lucky. We divided by half, but each half only have one single element in it. So the size of these problems are already 1. That means they're already sorted. So they're already, the pivot and low and high is like the same place. So we already know the position of them. So we're gonna stop. So both of these basically are done, right? So we don't have to keep doing anything else with them. Now we go to the other side, right? So you remember, this was another array that we had, and we had to start dividing, and find the position of the pivot and everything. So pivot is high, it's as 8, low and high. So we're going to do the same thing we do partitioning, right? So 9 is bigger than our pivot, so we don't like it. Low is going to stop right there. High is 7, 7 is lower than our pivot, we don't like it, so we have to do the swap. So 7 is coming here, 9 is going there. So we're doing it again. Low is pointing to 7, we're good. Then we move to the next. Low pointing to 6, we're good. So we're pointing to the next. And now low pointing to 9, which we don't like it. So we're going to stop right there. We'll start with high. High pointing to 9, we're good. And high pointing to 6, we do not like it, right? We're going to stop right there. But then look at it. Low and high passed each other. That means we did find the position of the pivot. And let's see another color I can find. So we're going to do the swaps. The 6 coming here, 8 going there, and we basically, it's kind of like we did sort the 8s. And we have kind of two sides in list. One of them is only one element, the other is 2 elements. It's not too bad. But since this one only have 1 element in it, it means that we already find a position of the pivot in this one. And so we cannot stop, right? Because it's only have size 1. So we're done with that one. So we're going to highlight that one as well. But this list still needs some work. So we had our pivot, and then we have a low and the high in the same place, which is fine. So we start with low. Low is pointing to a place that is bigger than our pivot. We don't like it. So low is going to stop right there. High is pointing to a element that is bigger than our pivot. So we're good. So we're going to go one more. And the high is going to stay here. Now high is pointing to element that is basically, similar to our pivot, but this also keep that in mind, the low and high pass each other. So that means we find the position of the pivot, and the position of the pivot is any place that the high pointing to it. So that means we find the position of that as well. So we did partition. One part is 0 and the other part is only have one element in it. And since it's only one element in it, that means we already find the position of it as well. So it's already sorted. So now let's see what we're going to do. Here, we're just going to put all these elements. I'm going to just get rid of all of these p and highs that we don't want anymore. So let's put them together. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this did sorted it for us and put them in its own position. So basically, you don't need extra space in this algorithm, as you can imagine. So it's happening inside this algorithm. The only things that you have to do is, you have to keep that in mind. It's not always going to act in log n because we're not always going to divide the list by half. So hopefully this demonstration that I had here was helpful for you to understand how this algorithm works. And so we have the animation as well that is, can be helpful a little bit. Let's see. The partitioning is going to be shown in this animation. So let's look at the partitioning part. So pivot, low and high. So again, low, whoever low pointing to it has to be smaller than our pivot. So that's an objection. Low stop right there. And high is 63. So we're happy with high. So high is going to keep going. 9. It's not a happy place. So we need to do swap. We keep going back with low. We're not happy. Low is going to stop right there. High is 93 is good. 70 is good. 36 is good. 47 is good. 40 is good. 48 is good. 18. I think swap is needed. Then we're going to go again back. 18 is good. 86 is not good. So we're going to stop right there. And the 38 is good. 0 is not good. To do the swap. So low pointing to 0 is good. 48 is not good. So low is going to stop right there. High stop at 6. We do swap. Low point 86 is good. 21 is not good. So it's going to stop right there. High point into 48 is good. 21 is good. It's go to 6. It doesn't like it. It's going to stop right there. But then look at it. The low and high passed each other. That means we find the position of the pivot. So we're going to have a swap between 6 and 18. So it's not going to go to the next round of this, but as you can imagine, now we have a list of 6, 9, 18, and 0 in the left side, and then we have another basically list of 21 now all the way to the 63 on the other side. So, and the last thing we want to do is for the quick merge sort is to do the same thing we did with the other algorithms, and that is going to be comparing it with the different data and if they are stable or not. You already kind of noticed that this algorithm is not really adaptive. That much because I know it's all based on how we do partitioning on it. And also it's telling me that it's not stable as well. So it's going to change the relative order of the algorithms. So let's look at this. You know, they're almost finished at the same time. So sometimes it's worse than the other. So I guess it's not really happy with few unique elements. That's going to really be a problematic for this algorithm because of the, you know, a lot of uh, and that's why it probably is not as stable, because it's going to keep moving things around. So it's not going to keep the relative order of their algorithm as well when you have some duplications. We have other algorithm that is really quick, but it's quick tree. I'm not going to talk about that. So it's basically, instead of having a one partition or, you know, dividing it by half, you know, we can divide it even more. So back to our slide real quick, just to make sure we're not missing anything in this case. So quick sort, just the partitioning part of the quick sort is going to take this order of n. But overall, in the worst case scenario, if there is completely reverse sorted, for example, and this will always, the pivots is going to be even larger or smaller element in the list. So we're always going to only reduce the size of the problem every time only by one. So those going to, like as a you know, other types of algorithm we see, like bubble sort and so on. So that's going to act as order of n too. But in base case, it's really going to act like a recursive types algorithm that divided everything by half. And in average case, they're both going to be the n log n. But we're not going to talk about the, you know, more about, you know, what is the average case, what's the base case, those kind of things. So we're going to just stop right here as far as explaining this algorithm. Just to know that the quick sort is using the partitioning algorithm and merge sort using merge basically algorithm to and they both divide and conquer strategy, and both have the complexity of n log n, but not always for quick sort. So that's one thing. That's something I want you to remember. The next algorithm is also a sorting algorithm. It's heap. It's also going to always act n log n. And also it's a very fast algorithm. But again, as I said, it's using a tree structure. So we first have to talk about the tree and different types of tree. And then we're going to come back and look into this heap algorithm as well. So we're going to stop right here. And so thank you guys and have a great day. Bye.